The problem of determining the area of a given surface is studied in the course of vector calculus, which we will see in a subsequent course of calculus. But using our theory of integration that we have developed till now, we could calculate some surface areas, and one of the particular cases that we will be interested during this course is what is known as surface of revolution. So what is a surface of revolution? So we have already talked about solids of revolution. What we have done there was that we had taken, for example, a graph of a equation y equal to fx, and we had revolved it around x-axis. So this is a very particular case. So this gives me a solid which is of this form. So what should then be surface of revolution? So instead of taking the whole region under this graph, if we only consider the graph of this equation, and if we rotate it about x-axis again, then the object that we get is called the surface of revolution. So if I want to compare it with the solid of revolution, you can see that you will have only the boundary or the surface of the solid of revolution that you are going to get. So let us look at some very particular examples. So first let me give you a formal definition. So a surface of revolution is generated when a curve C, a planar curve C, is rotated around a line in the same plane. So this 2 R2 is going to be the same R2. So for example, XY plane. So here what I have taken is a line. So y equal to, let's say, it's not x, but let me write x, and suppose this is our x-axis, this is our y-axis, and suppose we wanted to revolve this line, or the portion of this line, about our x-axis. So this will instead, if we had taken this region and revolved around x-axis, what we would have gotten is a cone. But here what we are going to get is the surface of the cone. So again, if I so this is so the surface of the cone can thus be recognized as a surface of revolution, which is obtained by rotating a curve. Here the curve is a line about another line, which is x-axis here. So this is the surface of the revolution that we have just got. So what is a frustum of a cone? So a frustum is what is as follows. So here again I have a line L, I have a part of a line. So we could even take y equal to x, and you could consider a part of this, and if you revolve it around x-axis, so this will give me a frustum. So a more formal definition is the following. So suppose C is a slanted line segment, which is P1 P2, which is drawn here. So let me call it C, and suppose that its length is lambda 2, as it is given in the picture, and suppose that C does not cross this line L. So it can intersect, but it is not allowed to cross it. So we could not have something like this. This is C, this is L. So this is not possible. This is not something we are considering. And suppose that the terminal points of this things are given by P1 and P2. Suppose that D1 denotes the distance of P1 from the line L, P2 denotes the distance from the point P2 to the line L, and by rotating the line segment P1 P2 around L, what we get is a surface of revolution, and that is called the frustum F of a cone with base radius d1 and d2. So you get a picture exactly like this. So one of the base, the bigger base has radius d2, and the smaller base has radius d1. So in one of your exercises, you will compute the surface area of the frustum that I have just described. So let us go ahead. So in the same difficulty that we had seen in the case of arc lengths. So here also we will not be able to concretely describe how would we come to a formula for the area of a surface of revolution. But so I decided to give you the formula exactly without spending too much of time behind giving motivations and other things. So here what we are going to take, we are going to take C, a parameterized curve. So we have seen the notion of parameterized curve when we talked about arc lengths. So suppose that C is a parameterized curve given by xt yt, where t belongs to this closed interval alpha beta. So if C is smooth, so what is a smooth curve? Recall that all we need is that xt and yt have to be continuously differentiable. So that is a differentiable function whose first derivative is continuous, and our condition remains the same as before, that C does not cross L. So, so suppose that L is given by this equation ax plus by plus c equal to 0 in the xy plane, and suppose we have this parameterized curve which is given by the functions xt and yt, the parameters, and suppose we rotate our curve that we have just got around the axis L, or around the line L. So then the area of the surface of revolution that we have just generated will be given by this formula. So 2 pi times integral from alpha to beta rho t under root x prime t whole square plus y prime t whole square dt. So what is rho t? So rho t is the distance of the point x t y t from the line L. So if pictorially, if this is our curve C, this is our line L, so this is a smooth curve by our assumption, and also one of our assumptions is that C should not cross L. It is allowed to touch L, but it should not cross L. So then suppose that this is our point xt yt. So we will draw a perpendicular from this point to the line L, and we compute this distance, and we know from our coordinate geometry, high school coordinate geometry, that this formula is well known. If L is given by the equation ax plus by plus c, then the distance is given by exactly this formula. So all we need to do is that we need to compute this integral 2 pi integral going from alpha to beta modulus of axt plus byt plus c divided by under root a square plus b square. This is the formula for rho of t times x prime t square plus y prime t square dt. So now we are going to look at some special cases, as we have seen in the case of arc length. So what are the special cases? So first of all, I have written down the formula here so that you do not forget about it, and we can also refer to it as and when it is required. So some special cases. First, suppose that I have a curve which is given by y equal to f of x, and I want to rotate it about x-axis. So this will give me a surface of revolution like this, and suppose we want to compute this area. As I have mentioned, that if fx, the function fx, is continuously differentiable, then the curve that we have, which is c, is going to be a parameterized curve. So it is continuously differentiable. So if this point is given by t, we have seen that this point is given by t comma f of t, and then we can just apply our formula. So just one more thing is that we have to compute this rho t, but computing rho t is, or I mean rho of this point, which is very easy. So what is the coordinate of this point below? This is t0, this is perpendicular, this line is perpendicular to our x-axis, and we can see that rho t is nothing but the y coordinate of this point, which is given by f of t. So one of the observation is that it could not be it could not be the case where ft can take both positive and negative values. It can take either non-negative values or non-positive values because of our condition that the curve c does not cross this line. Okay, so then suppose that, as I have said, f is continuously differentiable and our curve is given by y equal to f of x in the interval where x belongs to ab. And of course, our warning is that C should not cross L, as I have just mentioned, and as I have just indicated, that if x is either bigger than or equal to 0 for all x, and if x is less than or equal to 0 for all x, because C does not cross L. So then, if I just use the formula which I have written here, or which I have just described in my previous slide, we can see that this formula turns out to be as follows. So 2 pi uh, 2 pi f of t modulus of f of t times square root of 1 plus f prime t square dt. So what is xt here? So xt is t. If I take x prime t, that is going to be 1, so this is 1 square, which is 1. What is y prime t? Yt was equal to ft, and y prime t is consequently f prime t. So fair enough, all this formula put together gives me the area of the surface of revolution, which we have just obtained using this curve when rotated about x-axis. So in a similar flavor, if I have a curve which is given by the graph of the equation x equal to gy, where gy, the function g, is continuously differentiable, and all those conditions that g does not cross L, which gives me either g is always non-negative or always non-positive. So then we can see that the area of S is given by 2 pi times integral a to b modulus of gy times under root 1 plus g prime y whole square dy. So how do we get to this formula? So here an arbitrary point is given by g of t comma t. We have assumed that g is continuously differentiable, so is t. So our situation applies. So we are revolving our graph x equal to gy about uh, so x equal to gy about y-axis. So the equation of y-axis is given by x equal to 0. It doesn't matter. So if I pick a random point on in between y equal to a and y equal to b, which I call t, then the corresponding point is given by gt comma t. So the distance between this point and our axis of rotation is given by g of t. So we just plug in all these things here to get to our formula that we are interested in. So now, as always, let us look at some examples. Some of them are very interesting. So first we look at the case when we rotate a curve about x-axis. So we do not forget the formula that we have just derived. So 2 pi integral from a to b modulus of fx times under root 1 plus f prime x squared dx. So why don't we take a curve which is given by the equation y equal to x cube in the region where x varies between 0 and half, and we are going to rotate this curve about x-axis. So how do we compute the surface area? The surface area is computed by putting in all this information in this expression. So 2 pi modulus of fx, but here x is always bigger than or equal to 0. We know that fx is equal to x cubed, and this is always going to be bigger than or equal to 0, and in particular in this case where x lies between 0 to half, so modulus of x cube is going to be x cube itself. So fx is equal to x cube, which is always bigger than or equal to 0 in the interval 0 to half. So instead, if we had considered the interval to be minus half to 0, then it would have been always negative. But our warning was that it should not cross our origin, so we could not have taken the region where x varies inside the closed interval, let's say minus half to half. Okay, so all these things aside, let us now compute what is the surface area. So to compute the surface area from this expression, you could see that we need to make use of of our integration by substitution. So I have chosen this example so that it is so that you also get an opportunity to recall our method of substitution. So what is our method of substitution? I need two functions, f and phi. F has to be a continuous function, phi has to be a continuously differentiable function. So and phi of alpha beta should be equal to ab, the closed interval. So then something happens. So if I can if I want to integrate this function, f of phi of t times phi prime t dt on the interval alpha beta, then we are going to get integral of fx in the interval phi alpha phi beta. So here we have to choose our functions f and phi. I need f to be a continuous function, so let me take under root 1 plus x. Remember that all we need is this expression. So I take f of x to be 1 under root 1 plus x, and phi is the function 9x to the power 4. So what is f of phi of x? This is exactly the expression under the square root. What is phi prime x? Phi prime x is 36x cubed. You know how to derive this. So phi is a function from 0 1 half to 0 9/16. So the interval from 0 1 half is going to be changed to 0 to 9/16. And now if you do all the calculations correctly, you will come to this formula. So I want to emphasize that if I ask you this question in your exam, I would be very happy if you stop here, because this will give me an idea that you understand these notions. And if you go further and mess up calculations in order to simplify this expression, then it will not be very good for you. Okay, so we have got the surface area of the surface of revolution that we have got by rotating the curve y equal to x cube on the region as x varies between 0 and half about x-axis. So let us take an example of rotating a curve about y-axis. So do not forget this formula that we have just derived. So here I have taken a rather simple example, x equal to 2 times under root 4 minus y, as y varies between 0 and 15/4. So the surface area is exactly given by this formula. If you put in the formulas correctly and do the integration, which is quite simple over here, the final integration, you will see that the final answer that you are going to get is 35 pi root 5/3. One last example, something that you have seen in your coordinate geometry or insulation courses in your high school, is how do we compute the surface area of a sphere. So how do we compute it? So there are a few ways of doing it. So I'll give you two ways, so you can think of the third way of computing the surface area. So first I'll use the parametric form that I have talked about at the beginning. So what I do is that I take a sphere of radius r. So radius r. So remember, just for your information, that a sphere is given by the equation x square plus y square plus z square equal to r square. Okay, so what I do is I look at this picture. Suppose this is our x-axis, this is our y-axis, and I have a semicircle of radius r. So, and if I rotate this circle that I have just taken, so this is not 0, this is not pi, so this is not 0 or pi, this is simply 0.1 and minus 1, but you will understand why I had written down 0 and pi. But so the point is, if I have x-axis, y-axis and the xy plane, and if I take this semicircle, upper semicircle, whose points are given by cos t and sin t, the parametric points, Then if I rotate it about my x-axis, then I'm going to get the sphere that I am looking at. So so this is our L, and we are going to rotate this piece of semicircle about L. So how do we proceed about it? So we have taken this parametric form: x equal to r cos t, y equal to r sin t, as t varies between 0 and pi. And as I said, I want to look at the surface of revolution. So we know what is the formula. The formula is given here. The formula is given here. So what is the equation of the x-axis? This is given by y equal to 0. So axt plus byt plus c divided by a square plus b square. This expression is always going to be so using this formula, or using the equation of x-axis, this equation is always going to give me the following expression. So 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 how do you write this? So this is 0 times x, which is our ax, plus 1 times y, which is our b, and plus c, which is 0 equal to 0, right? So if you take so here x of t does not arise because a is 0. So b times y of t, so b is 1, so we will only have 1 times y of t, and c also is equal to 0, does not occur. And below we are going to have a square plus b square. We see that a is equal to 0, b is equal to 1, so this is going to be yt divided by 1 square, which is nothing but yt. Okay, so let me try to compute this now. So we know yt is r sin t divided by under root 1, and we are going to integrate. uh, so this was my x prime t square plus y prime t square. So what is x prime t? This is given by minus r sin t, so r square sin square t. If I take square of that, what is dy dt? That is r cos t. If I take square, it is going to be r square cos square t. And we integrate this from 0 to pi. 2 pi comes out, and if you do all the computations correctly, you will see that this surface area is going to be given by 4 pi r square. So this is our familiar formula that we have seen in our high school. An alternative way of describing this is as follows. So what do I do here? I take y equal to fx. So this is my y-axis, this is my x-axis, and suppose that this is 0, and this is r, and I take this function y equal to r square minus x square, and I say that if I rotate it about our x-axis, so this is our x-axis. If I rotate this half semicircle, let's say, about x-axis, then what we are going to get is a half sphere like this. And you could also do the same thing here, so that will give you a half sphere like this. If you add these two things up, then what you are going to get is the volume, is the area of the sphere, surface area of the sphere. And to get the area of surface area of this part of the sphere, you compute this. So there is a typo which I can see here. So this is going to be 2 pi r square, but 2 pi r square is the area of only one of the parts. So this part is also going to be given by 2 pi r square. So this is 2 pi r square, this is 2 pi r square, and the surface area of the sphere is just sum of these two quantities, and this is going to be given by 2 pi r square plus 2 pi r square, which is 4 pi r square. So that's all about surface areas, and in our exercises we will get some more examples.